advanced. It's a very important step in the sense that the most of the 5G advanced will contain like precursor enabled technologies for 6G. Okay, so that is how the technology will evolve. Similar to 4G to 5G. So 4G, then we have 4G advanced, then 5G. Okay, so similarly in the same fashion, we will again transition from where we are today, the 5G wireless, then the 5G advanced, and then 6G. Okay, so this is the ITU IMT 2030 6C vision. Okay, so it's a very important slide. This is kind of like constitution, you can imagine. So you can see on the left hand side now 6C has got like a hexagon. Okay, so because it's six diagonal and six corners. So in the six corners, what IMT 2030 vision statement saying is that they will focus on three important use case scenarios for 6C. So you can see integrated sensing and communication. It's very, very important area now for 6C. The reason is that the 6C is no longer just simple communication technology, it is intelligent communications. So intelligent means um, several devices deployed, and they basically communicate in an intelligent way. We'll see what that is. So intelligent integrated sensing and communication is a key area of the 6C wireless. Okay, so you can imagine that that's why I started with the first topic for the today. Then we move on to the right side, immersive communication. So immersive communication is your extended reality, augmented reality, virtual reality, all that high bandwidth, kind of real user experience kind of scenarios. Okay, so it's immersive communication, which demands quite high rate. I mean, the extended reality requires order of terabits per second. Okay, to sustain that kind of graphical user experience. Then move on to the right, integrated artificial intelligence and communication. So communication is no longer going to sustain on its own. So we have actively, the artificial intelligence penetrating deep into the communication world. So that's another kind of usage for the 6C, integrated artificial intelligence and communication. High reliable and low latency communication. So this is always be the pillar for the any communication network. It must be highly reliable. Without that, it's of no value. And low latency communication. So now we are talking about all real time stuff, extended reality, augmented reality. So all this needs very, kind of ultra low latency, because user demands something and he needs to get it in no time. Okay, so that's the kind of um, um, user experience we were targeting at 6C. Okay, then ubiquitous connectivity. So so the current wireless talks about a lot 5G, and we all know in practicality like what kind of connection experience we all get. So now 6C at least, I mean, is determined now. IMT is determined to increase the coverage and the connectivity on the ground, in the air, on the space. Okay, so I'll talk about all those aspects later on. So connection everywhere. You be in aeroplane, you be in drone, be satellite, everywhere. So it's like ubiquitous connectivity. And the last one, not the least, massive communication. What is massive communication? There will be a lot of IoT devices going to be deployed, all with lots of digitization being in the pipeline. um, Cars talking to each other, cars talking to drone, and drones talking to drones, and all these sort of massive number of devices. It's not only the traditional mobile, all sorts of cars, other devices, communicating intelligently, for a better world. Okay, so that's the six important um, areas that IMT 2030 is targeting to provide as part of the 6C wireless. Okay, so this is the real stuff. Okay, coming in the next few years. Okay, so so we are all communication engineers. So what actually the communication challenges, extension from 5G. So EMBB. So we know that it's targeted at the broadband stuff. A lot of data, targeting at the applications of the streaming, etc. From there, we are going into immersive communication. So it's a lot of extended reality, all that type of applications is 6C targeting it. And MMTC. So you can see there's like small, low latency, like NB-IoT, CAT-M, all these use cases will be turning into kind of massive communication. Be like millions of devices you are thinking at that scale. Okay, so then URLC, so reliable low latency communication. We have severe challenges already in 5G, so now that is um, becoming hyper reliable low latency communication. So this is where all these new use cases coming, real time surgery, and autonomous driving. You can kind of think, the amount of reliability that required, if car is being driven autonomously on the kind of hazardous driving conditions as present today. So what are the new ones? Ubiquitous connectivity, integrated AI and communications, integrated sensing and communication. Okay, so these are quite challenging areas. Now we are targeting at 6C areas. Now on the right hand side, you can see, so we have 9 capabilities that are already provided by 5G, and we are enhancing them as part of the 6C. And there are 6 new capabilities that are listed in the top blue color. So coverage, sensing related capabilities, AI related capabilities, sustainability, because this is like energy and all that comes into picture. Interoperability. So we have lots of technologies now getting deployed, terrestrial, non-terrestrial, open RAN, cloud, and is a need to, kind of provide the interoperability for all these independent and technologies. Positioning, which is traditionally provided by the GPS so far. So we are looking at the positioning as a new capability for IMT 2030. Okay, and the bottom 9 enhanced capabilities that are listed in the green. Security is a common aspect, privacy, resilience, reliability, latency, mobility, which is a crucial aspect of the 6C. So we'll talk about that mobility aspect in high-speed trains. So now even in India, you can see, as part of Atmanirbhar Bharat, so new use cases coming up, in fast-moving trains, etc. Connection density, as I spoke already, massive communications. You need lot of number of devices being connected to the network, so you need to have high density service need to be provided. So area traffic capacity, spectrum efficiency, user experience data rate. So this is the important aspect actually. So um, user experienced data rate is an important term, often being not happy with the existing wireless technologies. So from 4G to 5G, so people are not very clear. I mean, like what actually they get out of 5G when they subscribes to this kind of service. So that's why now this is being taken very important use case. So how much actually user experience it? Okay, yes, we talk about megabits per second, terabits per second, and all, but actually, does user experience all this? That's aspect we'll talk about later. Then the peak data rate. Okay, so how much when on a high demanded scenario, how much data rate that's user experiences and the peak data rate of the system. Okay, so this is the framework in which now the 6C activities will takes place in the next couple of years. Okay, so now we'll go to the the topics that we introduced earlier. So the frequency bands. Okay, so obviously the 5G can't operate in 6C. Sorry, 6C cannot go and operate on the 5G frequency bands. So we need a new frequency bands for the 6C to operate. So here I have illustrated, how the 6C most likely will progress on deploying, the frequency bands. So you can see um, it's like a kind of pyramid. Okay, so um, the first band that possible is like 7 to 20 gigahertz. Okay, so it's like centimeter wave. A lot of challenges in designing RF components. It's not walk in the park. Okay, so it's we'll see the challenges in later on. So the next band 75 to 110 gigahertz. So it's lower millimeter wave. 110 to 175 gigahertz is kind of like upper millimeter wave. The bands between 275 to 300 gigahertz, again it's upper millimeter wave. Then the important thing that the wireless industry is now actively researching is terahertz. It's a new technology, in the sense that so you can kind of see now, we are stepping into terahertz frequencies, which we never talked about 10 years ago. Okay, so we kind of thought that is like infrared kind, light communications, etc. Okay, see the disadvantage, as we go along these frequencies, so there's a huge challenge in front of us in designing the RF components, because your wavelength reduces significantly. So then you have a huge challenge of designing your components, antennas, the antenna arrays for massive MIMO communication, etc. I mean, we all know that the centimeter wave kind of provides good coverage, but again it can't provide large bandwidths required for kind of 6C use cases. So the bandwidth, you can kind of now see, I mean, 5G, the maximum is like 400 megahertz, right? It's still not deployed yet, but you kind of like 100 megahertz normal 5G, so you can kind of like 200 megahertz carry, I mean, and then the next is 400 megahertz. Here you are now see like, starting 400 megahertz, going up to like a terahertz kind of bandwidth. Okay, so it's not like carrier frequency anymore. Okay, so you're thinking about that kind of bandwidths to provide 6C communications. Traditional electromagnetic spectrum, I just want to show where we are right now, so you can see um, The traditional communication started with like amplitude and frequency modulation, transmitting radio waves, evolved into, wireless communication in gigahertz. Now we are going into, the terahertz. Beyond that, you can see the infrared rays is the next spectrum. And the next is the important point. Okay, so you can see if you have to go beyond infrared, so the spectrum is visible. Okay, so it's light, um, and that's where the important transformation comes into picture in future. It's like optical wireless communication is not far off. Okay, I mean, it may not be realizable in 6G because we have still some spectrum like left in terahertz. But once the 7G comes up, then you don't have kind of, no option to but go into optical wireless communication where, the spectrum is visible. Okay. Right. Okay. So that's the kind of background. So, so the message, I think, the industry community now trying to arrive at is that the 6C on day one is not going to look much different from 5G, because that's not good if it does look quite different from 5G. So it will be like, higher frequency bands, um, more bandwidth, and that gives lots of data rate. That's how it will start. Okay, so it will be like similar to 6G, but will be like a lot higher bandwidth, lots of data rate, connections everywhere. Okay, so that's how it will start, like a first a baby step, and then it just builds on, on top of that. So that's the kind of. So you can see here 6C uh, is a quite a bit of new things are coming into the play here. Okay, let's look at carefully. So this is what is called ubiquitous connectivity, as one of the that hexagon, corner that we have discussed earlier. So here you can see your traditional base station. Earlier it was actually, connecting to a mobile, um, and then to providing communication link to another device is no longer, limited to that kind of use case. So now you see autonomous vehicles, communicating over V2V interface. So you can see, the vehicular to vehicular communication, vehicle to network communication, that is V2N, then V2I. So when the vehicles are moving autonomously in the field, so they also need to know the traffic signals. Otherwise, it will be a big chaos in the deployment. So V2P, so vehicular to person communication. Um, because when you book a cab, obviously, the intelligent part of the car, communications need to communicate with the people, so V2P. And then, so the base station needs to communicate to another base station, so that is like P2P. And then we have new stuff coming in. So the drones are now kind of like being active service providers. So being deliveries, to the remote areas and, other parts. So the drone communication is going to come. Okay, and then we spoke about terahertz access point. Um, so the terahertz is basically kind of very small coverage area, right? Because you are going at large frequencies. Obviously, the coverage area will be very small. The bandwidth will be like massive amount of bandwidth, and, like massive amount of data rates will be, provided to this users with, like augmented reality, virtual reality, and all these kinds of user experience based use cases. Okay, so now you have a connectivity that comes to the terahertz access point into the base station. So you can see the amount of different kind of channels that are in the system, that the technology that needs to deal with is enormous. um, so the one thing I haven't shown here at is satellite. Okay, so and the terrestrial to non-terrestrial, and again to the ship and the aeroplane. Okay, so all these channels are of different nature, um, and needs different kind of channel coding, and equalization and delay Doppler, like multipath and fading profiles. Okay, so the you know getting grips with the kind of channels that 6C is aiming at itself is a area of complete research. Okay, so here, so we kind of just pause video, and then explain what is actually part of this video. Is that so we are kind of like, this is VRV. Okay, so we are actually trying to kind of like propose a complex use case here, like for mobility management. Okay, it's a handover scenario. um, so user is basically is sitting in the high speed moving train, and being connected. You can see here, is connected via LEO satellite, and then the satellite actually connected to aerial vehicle which is providing base station services, and then connection into the user and a train. Now the train is moving very fast, so you can see the like amount of multipath channels that possible, from the buildings, from the atmospheric scattering, all that, um, and then eventually he's approaching a station. um, then he will be handed over to ground based station, and then which is providing a connection into the train. Okay, so that's the kind of use case we have kind of trying to portray here. So you can see the number of multipath models, reflections that is coming from different buildings, all these things. So you need an effective modeling of these channels. Yeah, so the video starts here, so you can see from satellite and coming to drone, and then to the user in the train, and then he's approaching kind of like a base station on the ground, um, and basically obviously the handover will happen to the base station, because that's like in today's world it's a reliable link. Okay, so you can kind of imagine the amount of challenge in modeling all these channels in a real time way. Okay, so we kind of like covered. So what are the objectives of 6C? What we are, IMT 2030 vision, saying what it will provide as part of 6C. We kind of visited, the complex 6C network modeling and the channel use cases. Now we'll slowly look into like what kind of technologies required to provide this kind of service that IMT 2030 aiming in as part of the 6C. Okay, so you can see, the technology actually evolved, for last 30 years, from first generation and second generation wireless into 3G, 4G, 5G, and 6C. Okay, so the important being the waveforms, and how the resources are being used, which kind of suggesting multiple access technologies. So you can see in a very primitive case, where the frequency is divided and then allocated to one user, whether that user is required that frequency all the time or not. Um, there's the frequency division multiple access, time division multiple access, and then the 3G is CDMA. So that's where I started my career. Okay, so with third generation wireless, with being code division multiple access, which is your traditional WCDMA. To 4G and 5G is basically using orthogonal frequency division multiple access, where the users are allocated both frequency and time resources. Okay, so that's most efficient way compared to TDMA and FDMA. Okay. um, um, and it's a good access technology, OFDMA. So it survived 2 decades, that's serving 4G and 5G, two successful wireless technologies. And then now the 6G. So what's the 6G, is the question mark, right? So today there's nothing that is standardized yet. So whatever we speak today is all speculation. Okay, so let's be clear about it. So what are the 6C candidate multiple access technologies? What's the industry is excited about it? Okay, what they are guessing and speculating. Okay, at this stage. I mean, we can't rule out, the WaveDM still being continuing into 6C. Okay, so it's great technology. It provided good access so far, 4G, 5G, and it's potential candidate for 6C as well. Um, and then another potential candidate is like orthogonal time frequency space, and then the next DFT spread OFDM. Okay, so these are the potential candidates, and the multiple access technologies we have. Again, OFDM resources are divided into multiple uses called OFDMA, also called as SDMA, and another one important is NOMA. Okay, so this is the thing that is actually making some noise in the research area now. I mean, NOMA is actually also there in 5G, in a part of research, but it never got into specifications because, for the reasons known well to the community. The other one we are thinking, I mean, is like RSMA, rate split multiple access. Okay, so on the right hand side, I illustrated what a good waveform requires. I mean, I don't need to talk about to the audience, so they are well aware of it. So you need more spectral efficiency, robust to channel conditions, good PAPR, so that the RF design is simpler. Um, okay, and then requirements, complexity, flexibility. And again, RSMA is like middle ground between NOMA and SDMA. So we'll talk about that. Okay. So what is OTFS? I mean, I don't need to talk about OFDM, right? We all know OFDM. Okay. So let's talk about something new. So the OTFS, orthogonal time frequency space. So what is the drawback of OFDM is OFDM is very sensitive to the intercarrier interference. So we all know that it's not perfectly orthogonal. It is orthogonal to some extent, but as long as your channel dispersion is bigger, then you have interference from the adjacent subcarriers. Okay, so you got there's a limit for OFDM being orthogonal. Okay, so that is where now the OTFS coming into picture, because 6C is aiming at like complex use cases like high mobility scenarios, where OFDM might not cope with it. Okay, so so it is OTFS is basically, you can think of a um, multi carrier OFDM. So it's basically OFDM, and we have small um, transform domain built on top of the OFDM. So that's where we look at. So you can see here, on the top block, from the right side we will describe. Okay, so you see add CP parallel to serial IFFT. Okay, so you know all this. Okay, this part of the OFDM. So the OFDM is basically in frequency time domain where your processing is located, and you convert it into time domain, and you transmit and add cyclic prefix and you transmit. Okay, so that's the standard OFDM technology. So now you see on top of the OFDM, so now you have another transform, which is a two-dimensional transform, which is called um, inverse symplectic finite Fourier transform. I'll talk about it. Once you understand this, then it makes sense why OTFS is a potential candidate for 6C. Then the pilot insertion. So the pilots are unique. Um, it's not similar to OFDM kind of pilots. It's a new research area. How the OTFS pilots will be designed and inserted into the grid. Then you can see, so whatever your traditional OFDM frequency time domain is actually delay Doppler domain. Okay, so you can kind of see why the OTFS is a promising candidate, because the signal is in delayed Doppler domain. The channel is actually, the characteristics of the channel is actually the delay which is coming from multipath, and the Doppler which is coming from the moving aspects of the connected device, be the UE or the train or some other aspects. Okay, so it's a classic scenario where you can actually represent your channel is actually in delayed Doppler domain, which is actually the physical world, of the UV. Okay, so that's the quick basic introduction. So you kind of like frequency time domain, which is your OFDM, put one step above, which is basically delayed Doppler domain. Okay, so on the in the receiving side, it's a similar again, your traditional OFDM reception. You receive your time domain signal, convert into frequency domain by using FFT, and then one step more. Okay, so you simply fast Fourier transform to get into delayed Doppler domain. Okay, so then you kind of, your signal is what is transmitted in delayed Doppler domain. So you need to have the problem of again channel estimation and equalization to mitigate the effect of the channel, and then go to the demapper, deinterleaver, and LDPC decoder. Okay, so that's the quick introduction. So what is ISFFT? I mean, it's a big area. So again, we'll start from the bottom. So you can see this is the at the bottom your transmitted signal, and then kind of like frequency time domain signal, which is your OFDM. Kind of 550, right? So frequency time domain conversion to time domain. So one step, second step, and then if you go to the one on the left hand side, so that's where your ISFFT comes into picture. Okay, so it is simple one-dimensional transform, both in delay and Doppler, to get into frequency and time domain. Okay, so I mean it's not difficult to figure it out what is exactly. Um, so you can kind of say you mapped your delay Doppler grid with your modulated symbols, and you do kind of like row wise transforms and column wise transforms to get into your frequency time domain. Okay, so that's kind of very simple one dimensional transforms. Okay, so you can see time domain, frequency time domain, and then you get into delayed Doppler domain. Okay, so which is a new domain. None of the technologies 5G, 4G, or like even the other US wireless standards hasn't adopted delayed Doppler domain yet. But if it does, it's a classical way of dealing, the channel impairments actually. What are the challenges? Okay, so you have a pilot design, channel estimation, data detection and equalization, and it's demanding. Okay, so it's more processing, but you get kind of good results. So you can kind of see at the the Doppler shift is becoming larger. The OTFS performs better, and the OFDM starts um, degrading the performance quite rapidly. Okay, so okay, rate split. Again, it's a very good multiple access. So it's a kind of middle ground between NOMA and this one. So I assume you all know NOMA. NOMA is basically non-orthogonal multiple access. It's a very simple technology. All resources allocated to all the users. So it's like non-orthogonal communication. Okay, and in the uh, highly efficient, but the complexity, the penalty that you pay is that the receiver is very complex. So because it's non-orthogonal, so you have to kind of estimate all the user signals, and then you have to successively do interference cancellation before you decode the user signal. Okay, so it's highly delay sensitive, and also complex receiver. On the other hand, we have like orthogonal multiplexes, which we have, SDMA, OFDM, um, kind of spectral efficiency degrades. Receiver is easy to implement. So now we have RSMA is like a middle ground. I'll quickly go through it. I think we are running out of time. So we have like two users. I have taken this example, which are trying to transmit the data over the wireless communication protocol. So here what happens is, uh, uh, so the two user signal is actually split into two parts. So one is common part and other is private part, and that is done for both the users. So now you can kind of have common part for both the users, which will be combined, and then again traditional encoding. Okay, and then the private parts are encoded as it is without any changes. You can kind of see n plus one streams are um, for the common users. On the receive side, so you can see each block is one user. Okay, so you can see on the right hand side, so the first block is user one and the second block is user two. So now you can see inside the user one, so the user one has to decode the common part, which is like multiplexed for all the users. Then you can split it. Then you can kind of extract that user signal, and then again you kind of reconstruct all the signal again, and you do interference cancellation. Okay, and you decode your private kind of stream. Okay, so common stream is decoded as it is, and then you user extract the common data from the stream, and then you reconstruct it and then do interference cancellation. Okay, so that's the kind of receiver structure. It's simpler than NOMA, but little ugly than like your orthogonal multiple access. But you get gain. Spectral efficiency will be higher because all the common users are overlaid over the private resources. Okay, so that's the more resource usage. So here we have did an active research via wireless in collaboration with universities. So we have developed VRV IPR. So we have published quite a few papers in the areas of research, rate split multiple access. You can see here on the right hand side. You can access this paper in IEEE, transactions and wireless communications. So you can see here at particular average SNR. So you can see your RSMA performance is linear. Okay, because as the signal SNR increases, the other technologies actually saturates, and then whereas the other one just keeps going because as a higher SNR, so you can actually increase uh, you know um, the data rates that actually part of the common stream. Okay, so you get more and more spectral efficiency. You can, um, so the other area that we go on is integrated sensing and communication. Again, this is another hexagon. Okay, so so here it's not only the communication. So sensing is also an important area. Okay, so you can see here I have illustrated two use cases where the network is sending both communication signal and sensing signal, whereas users are actually sensing these targets. Okay, and in the other case where the network is sending, and then the network itself is sensing the signals. Okay, so it's not only communication with the connected devices. So the network now also wants to sense the non-connected devices. There may be like buildings. Buildings, it's like objects. Okay, so they don't communicate. Okay, so but the network is sensing all these obstacles, objects, and other things in the channel, so that it can optimize the network, optimize the way it transmits the signals, the beam direction, all those parameters. And 3GPP outlined all these kind of use cases for sensing. You can see monostatic, bistatic scenarios, where base station sends the signals, whereas the UE detects them, or the vice versa. What are the use cases? So what you do, do with sensing information? uh, you can kind of detect the human activity, and the human activity recognition tracking, like safety, like anybody intruding into the building, anybody trespassing, the hazardous area, all this activity and tracking is an important use case for intelligent communication. And aerial vehicle detection, if some uh, unidentified or unwanted drones are coming into your area, so you can actually detect these aerial vehicles and their trajectory, traffic management, environmental monitoring, digital twin, and then better communications. You can form effective beams. You can see where the users are. You can form the effective beam spots in that area. um, all comes with again a complex, so you need intelligent receiver, does both receive the signal from the communicate device, and also from the sensing, reflections from the objects, and process all this information. You need like effective resource allocations for the sensing signals, good waveforms like OTFS, and intelligent beamforming. Okay, so this okay, so the another hexagon thing. Okay, so we have integrated AI and communications. Okay, so the AI is now going to be penetrating deep into the daily life of the communications. It's inevitable. Okay, so kind of like developing all these complex neural network models, to do the AI modeling. Okay, so this is the 3GPP baseline kind of framework. Okay, um, so you have a data collection agent which collects all this complex data from the wireless system, which is from the user equipment, from the objects, and it kind of provide the inference data to the model, and the model is actually analyzing all this, and giving actions to the wireless communication system. And again you keep train the model with the training data, and then all the feedback, it's like a closed loop system, right? So at least 3GPP has actually defined all this framework, so that it won't end up with diverging models. Okay, so these are the three use cases that have been defined. But I imagine a lot of use cases will keep coming, in future, as part of the AI. So the first thing is energy. Okay, so it's a resource. So you need to optimize the energy saving, mobility optimization to minimize the handover failures, and have a better user experience. And you kind of load balancing, kind of shift the users into different networks, to balance the load, so that they have a better experience. All these are from 3GPP specifications, okay, which is going to be part of 5G advanced. Okay, so you can kind of see there are, trying to see where this training models and all these models are going to be deployed. Which part is it, RAN or is it OEM, maintenance network. There's quite a bit of study will happen in the next couple of quarters, to again. So the machine learning again, so you kind of like, this artificial intelligence keep learning about, your channels, how the channels are present, what kind of situations are there. Then it will adapt, all this beam forming modulation, and all this kind of to optimize all this communication aspects. Again, semantic communication is another solid area that is coming up. So I'll just give you an idea. The semantic communication is actually, they are aiming to break the Shannon bound. Okay, the typical like communication channel transmits what is this much data rates. It can't go beyond that kind of Shannon limits. Okay, so the semantic communication is, I think, is taking up the challenge, to just going trying to break the Shannon bound. Okay, so all this like knowledge, they kind of builds into the AI model. Okay, so when the users are communicating, okay, what they are kind of communicating, like all this kind of redundancy information that builds into the traditional communication information. So they build into that model. So when the similar kind of sequences are coming up, so they don't transmit the entire data. So they'll just say, okay, so the code words kind of communication, thereby you kind of transmit less data but convey more information. Thereby you kind of challenge the traditional theoretical bounds of the channel. Okay, again it's the same thing, it's still evolving. Okay, semantic communications, it's a um, and so now you can kind of see, we are talking about quite a bit of processing and all, um, kind of like AI models, and machine learning algorithms, and OTFS being in a very complex kind of receiver. So now you need to have like a new computing methodologies as well. Otherwise, all this research will be still in the paper. Okay, so it won't go into the practical world. So you kind of like cutting edge CPUs, server technologies. Nvidia is working on the GPUs, going to revolutionize the processing aspects. Like new aspects like TensorFlow and CUDA programming, all this. Okay, so will be new areas of research and things. Okay, so that's the talk. Um, Thank you very much for the opportunity. It's a good that I mean the industry is connecting with academics. Okay, so that's I conclude the talk with that.
Thank you so much, Venkatesha sir, for the great presentation and for clarifying. I think we have some doubts as well, but two questions, I believe. If you can just answer them. One of them is like, what is HR, which is asked by Aditya Yadav.
Yeah, it's a kind of like so your body kind of like a metric kind of thing. Okay, so you're kind of sensing all your surroundings, and that like high resolution imaging actually. Yeah,
Okay,
so
and one,
it's a high
yes.
resolution image, that you can kind of like like high precision, high resolution image which needs a lot of data to achieve. Yeah.
Okay, another participant, he wants to know the frequency band for 6G.
Yeah. Okay. So right. Well, let's go to that slide again. Yeah. So my screen is still shared.
Yes, sir.
Okay. So this is the. I mean, see, let us say. So there's a separate body that allocates the frequencies. Okay. So it's not the IMT. Okay. So it's I think. This is a separate body that allocates. So they are meeting. I think very soon to finalize the frequency bands for the 6C. Okay, so all these are candidates still. Okay, so it's not finalized. What these are the bands that the 6C is going to use. So you can kind of see here, it'll start with 7 to 20 gigahertz. So you can see 6 is already into, 6 gigahertz, right? So 6, up to 7 gigahertz is already, 5G is occupying. Okay. So we are thinking, the logical step would be like from 7 to 20 gigahertz, is like centimeter wave is the first deployment of this 6C basically. Okay. So that's where, um, uh, again, I'll revisit my point I said earlier. So the 6C, when it comes into the field, this, version 1 will look similar to 5G, but it'll be like higher frequencies because it can't reuse the 5G frequencies. So it'll be like 7 to 20 gigahertz kind of the frequencies, and it will be a lot of bandwidth, and the users will be allocated in a lot of bandwidth, be it OFDM, OTFS. So thereby they get a lot of user data, and hopefully and simultaneously we'll have good applications like extended reality, augmented reality, and then the device to device communications will uh, the applications will develop in parallel to provide the user experience to the users, for this massive data rates coming into picture. Then it will slowly migrate obviously into like millimeter waves, and the terahertz. So the terahertz eventually is a long term goal. Okay, so terahertz is not going to be on day one. Okay, so the terahertz will come slowly, and eventually into 6C. uh, the reason the terahertz is important is because at that frequencies the sensing resolution is quite high, so you can actually sense, and the resolution between your objects is quite good. So you have a very good sensing aspects. But the communication, that, right? I mean, it will be like the coverage shrinks, and then you have like small cells, kind of things. But your beamforming is very granular, very narrow, and pencil beams you can target it. Yeah. um, yeah, that's the kind of evolution that will happen.
Okay, so one of the attendees wants to know, can you please provide the like the presentations, the PowerPoint presentation to the participants?
Yes, I mean, it's already recorded, so hopefully that recording will service. But I'll also provide the slides. I mean, I ensure that we have nothing VIA specific on the slides, so yeah, we can provide the slides.
Sure. Thank you so much, sir.
Yeah.
And thank you, Dr. Hema Kali, for liking the session. As she has mentioned, thank you, sir, for the very valuable and informative session. So I believe anybody else, is there? Apurv, I think the questions, these are the only questions what we have. Or one second, I think there are a few more questions. Okay, Atul Tiwari wants to know, sir, what about the job scenario in 5G? Industry is not ready to give opportunity to freshers. How we can approach ourselves to be part of 5G team of any organization as fresher?
Okay, so difficult question to answer. I mean, um, well, I mean, the industry is currently, I mean, I don't know, the freshers coming out of the university now. Um, the industry is going through kind of a bit of slowdown, right? Not because that it's the fault of the communication technologies or communication world. It's just the general kind of uh, scenario. Okay, so um, so the way to get into this kind of industrial thing is basically you kind of up to date with what the industry needs are, what they're using, like programming languages, and they're using technologies like OFDM, and like NOMA, all this kind of and now the AI machine learning is also going to play a key role in the communication. So it's good to learn the kind of AI machine learning models as well. Yeah, so with all this, I think you build up the knowledge and skills required for the industry. Then obviously, that's what industry is looking for, right? The right kind of person, to. Uh,
Okay, there's another question. It seems wave band for 6G and are same as 5G. Please differentiate.
yeah, yeah. So, like for example, so here, so the millimeter. This is the diagram, right? Will be actually not completely utilized by unused bands. Um, Basically, the community, I mean, negotiating kind of thing. Okay, for the 6C technologies. Okay, that's correct. Okay, so the 5G is not using the entire, like every kind of megahertz, for the communications. Okay, so the unused aspects. See, because 6C, so we'll have to, as I said, has to progressively evolve. Okay, so you'll go with the kind of the RF technologies, and the kind of like 5G is already using, um, but with lots of bandwidth, new modulation waveform, new use cases, so that operators also need to embrace the technology, right? So they are the ones who is going to pay for all this. Okay, so they need to like the transition as well. So we kind of go evolve in that, like the known terrain into, slowly into kind of terahertz range, where 6C is aiming to go. Okay.
Okay, we have another question. One of the attendees wants to know 5G is still not deployed completely, but 6G is coming. Do we need 6G now until we are not completely able to take care, to take the benefits of 5G?
Um, I mean, see, we don't, we are not like, I mean, it's not like that. Okay, so the 5G is kind of like getting deployed. Okay, so India is actually, I mean, I think giving a projection that by next couple of years they want to cover 5G very much across the geographical world. So don't think that the 5G is going to go away, okay? Just because now we started thinking about 6G. So the 5G will be there, and then we are will be deploying, will be using 5G. Um, so so one thing I think I haven't mentioned is the timelines for 6G. Okay, so 6G is kind of like now in the research phase. So the specifications will start from 2024 onwards, 2024 and 2020. That's like next year. So that's where the specifications will start, and then the deployment of the 6C, you are looking at 5 years from now. Okay, so 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 there's as I mentioned, there's an intermediate step, also called 5G advanced in between. Okay, so we will continue to deploy 5G. So the operators continue to monetize the 5G access technologies. But again, we need to start studying. Okay, so what are the challenges that we faced in 5G? Okay, and then we need to solve. We are preparing the stage to solve those problems as part of the 6C. So for a prosperous world tomorrow. Okay.
Okay, thank you, sir. So I believe, okay, can we have DSP processors for real-time signal processing? Example, TIC series.
Yes. So I don't want to talk about specific things here because it's a general talk. So the way the technology, the processing technology evolved is, like in 3G times and 2G times. So we have a good signal processors um, with like parallel like SIMD instructions, right? That is standard, single instruction, multiple data kind of thing. Okay, so as the signal processing starts evolving, okay, so that kind of frameworks not able to cope up actually. Okay, so there are several reasons. Okay, be it memory technology, be it challenges in kind of caching technologies, etc. Okay, so then so now we kind of like uh, specific processing hardware platforms to general purpose hardware platforms. Okay, so that's the kind of flavor now we are in the sales, like you say cloud computing. Okay, so the cloud computing doesn't attach to a particular processor. Okay, so it's a general purpose processor. Okay, so your algorithms and your computing should be happening on any processor. Okay, so that's where some of the people able to successfully do the transition in terms of computing platforms, Intel, AMDs, and all these things. um, and then even we are now running out of that because the artificial intelligence model, machine learning models needs massive data. Okay, so they kind of like you know terabytes of data, processing, it's all data. Okay, so you need kind of like like massive parallel devices, kind of like things, that GPUs, for example. I mean, I'm not saying GPU is the platform. I mean, like GPU, AMD, they're all, in the race, to say, okay, so how do we actually, parallelize all this kind of data processing, and make sure that they can still meet the latency requirements demanded by the 6C. um, so this is where that first question, somebody from pressure, how do we get into the industry? Okay, so you need to kind of stay on top of all these latest trends and technologies, and how the computing world is evolving, and how technology world is evolving. Okay, so yeah, so this is the kind of thing. But
Thank you.
but
Okay.
yes, I think there are challenges. You know the computing platforms, but there are innovations as well in that area.
Okay, thank you so much, Venkatesha sir, for
Mhm.
clarifying the doubts and for the great presentation once again. It was a
Thank you
great
so much.
pleasure to
Mm.
have you with us. And
Thank
I
you.
would also like to like all the attendees, they must be learning significant points about the emerging technologies from our webinars. Now, I would like to invite Kaushalendra sir, Chief Mentor of the IoT Academy, to give a thanks note to Mr. Venkateshwara. Over to you, sir.
Uh, Thank you, Prabha ma'am. So thanks a lot, Venkat sir, for giving your valuable knowledge to all of our audiences. So I have seen you after a long time. For all the audiences, Venkat sir is my senior from IIT Kanpur, and we had worked together in Ubinetics while we were in UK, United Kingdom. So I also, since I have moved to use case development instead of working on layer one, physical layer, for quite some time. So there were few many new things that I also learned today. Sir has very well shared the knowledge from IMT to 2020 to IMT 2030 evaluation, and the wheel diagram where we had seen different six dimension aspects of 6G, and nine capabilities that are coming from 5G and that are being enhanced in 6G, and six new capabilities that are being proposed in 6G, and different frequency range we learned today, and the complex part is RF component design as we move towards the higher frequency bands. So that we also learned, and 6G channel models where like we learned various connectivity models like V2N, V2P, V2V, V2P, V2I, and mobility management use case that sir has shown when high speed train is moving, and the seamless connection or ubiquitous connection would be done from satellite to UAV and then to the user sitting in the train. So I think all of and some interesting new things that new dimensions that are being used, like ISAC, integrated sensing communication subsystem, that was new to me, and it is quite interesting for research area and for the product development also. And then AI ML modeling, since the 6G is going to be very very complex, even complexer than 5G. So definitely we need AI ML model to manage all the resources. And then the semantic communication, that is really quite interesting, that how we can send less information for uh, instead of sending the complete bigger one information, less information, and similar things we can receive at the receiver side. So these are the quite new things we learned in 6G. So thank you so much, Venkat sir, for giving your valuable time at a very short notice. You traveled back from Malaysia yesterday, and today you were able to manage all the things. Thank you so much, sir.
Thank you, Kaushal. It's honor actually for me to speak. Thank you so much.
Okay, thanks.
Thank you,
So,
Venkat.
so now, Venkat sir, if we would be continuing with the some live demo about the 4G 5G setup, and Nitin Jain sir, that is also senior to me. He was working in Session. He would be demonstrating the demo. So Venkat sir, if you want to stay, you can stay. Otherwise, it is up to you. Like whatever you want to like do.